Please start it.
As well as promoting techniques among undergraduate students to make them interested in the respective fields. For the welcome speech, I invite Ms. Nanda KP, Vice Chair, IEEE PELS SBC NSSCE. Over to you, Nanda.
Hope I'm audible. Good morning and good evening to one and all present. To have given the opportunity to welcome every lecture program organized by the Power Electronic Society, IEEE SB NSSCE. To begin our session with, I, on behalf of Power Electronic Society SBC NSSCE, heartily welcome our speaker of the day, Professor Udaya K.Madawala. We are extremely honored to have you with us today, sir. I would also like to welcome Dr. Bijana Kunju, Chairperson, IEEE PELS Joint Chapter Kerala, to this gathering. I'd like to extend a warm welcome to Dr. Vasandi V, a pillar of support and chapter advisor, IEEE PELS SBC NSSCE, and Mr. Abhinav Rajiv, a multi-talented mentor. Last but not the least, I welcome each and everyone present here and wish you all a beautiful session ahead. Thank you.
Thank you, Nanda. Next, let me invite Dr. Vasandi V, Advisor, PELS SBC NSSCE, for the presidential address. Ma'am is a constant supporter of all our activities of IEEE PELS SBC NSSCE. Over to you, madam.
Thank you. A very warm greetings from IEEE PELS SBC NSSCE. Today we are very happy that the first DLP of PELS SBC of NSSCE is about to start, and we are lucky enough to have the best person with us to start with. So Professor Udaya K.Madawala is an expert in the field of EV, wireless power transfer, and is the right person to talk on the topic grid integration of EVs and wired and wireless power transfer. Welcome to you, sir, on the behalf of IEEE PELS SBC NSSCE. And also we have with us Professor Bijana Kunju ma'am, who is the chair of IEEE PELS Joint Chapter Kerala, who is a constant supporter for all our activities. Once again, welcome to you, ma'am. Our PELS SBC started in 2018 and has been very active with so many programs for the benefit of student members and also professional members, and also for the benefit of society. So this is the first DLP from SBC, PELS SBC NSSCE, and I wish all the attendees very best wishes, and also I congratulate all the student members and also all the members who are behind this to make this event fruitful. Thank you.
Thank you, madam. Next, for the keynote address, let me invite Dr. Bijana Kunju, Chair, IEEE PELS Joint Chapter Kerala. The support and encouragement from Dr. Bijana Kunju and her team from IEEE PELS Joint Chapter Kerala cannot be expressed in mere words. It is always a pleasure to have you here. Over to you, madam.
Very good morning to all present here, and a warm greetings to Dr. Uday. In fact, when we saw the topic itself, we were so excited to listen to you. And when we were actually, all the researchers who are working in the grid integration of renewables particularly, as well as the electric vehicles, we look forward for the complications that we face and the challenges that we face in converter designs and the operating strategies that we choose for each case of research. And we always look forward for the words from an expert who will be clearly saying why are you choosing this value and why should you choose such a strategy and so on. So it is always a great pleasure and honor for all of especially the charging technologies. Specific reason that we are looking forward for e-mobility as a motto for Kerala state as well, in particular. And we look forward for converting most of our vehicles into e-vehicles in the next 2 years as a motto of the state as such. So if we are going for that, we need to develop a lot of charging strategies for
the felicitation. He has always been a great inspiration to us, both in our academics and in IEEE activities. Over to you, Abhinav.
Hello, am I audible now?
Yes.
Yeah, thank you. Thank you for that. So very good morning to all. As we all know, the pandemic has flipped every sector, and so do the academia. Providing accessible knowledge has always been a key element for the working of IEEE. The IEEE Distinguished Lecturer program is one of the most exciting offerings available to the IEEE Society chapters. Each year, the IEEE Power Electronic Society selects a few distinguished members of our profession as distinguished lecturer. This not only celebrates and honors their achievements in the field of power electronics, but also supports the PELS chapter activities by providing high-profile speakers for local chapters and section events. On behalf of the NSS family, let me cordially welcome and wishes. Let me extend my cordial welcome and wishes to Professor Udaya K.Madawala, Professor, University of Auckland. Sir, we are very much happy and proud to have you here in spite of your busy schedule. Hence, we are also looking forward for further collaborations with you in the future, sir. We are also very glad and very looking forward for your distinguished lecture on grid integration of electric vehicles. Being an NSSCN, it always gives me the immense pleasure to get back to where it's to Vijita ma'am, Vasanthi ma'am, and Bijuna ma'am, and all the faculty members who supported the team to commence such a prestigious event. Without further ado, I wholeheartedly invite you, sir. Thank you.
Okay, thank you. Can you hear me? Can you all hear me?
Yes, sir. Yes. Yeah.
All right. Okay. So first of all, I would like to thank the organizing Hello. Okay. I would like to. Can you all please? I would like that when I'm giving a talk, and if you can, I can mute from my side, and if you can mute your microphone, and that would be good. Otherwise, I'm getting a lot of noise from this side here. So first of all, I would like to thank everyone, especially the organizing committee, for giving me the opportunity to talk about what I've been doing for the last decade or so, and especially in relation to the wireless EV charging or wireless power transfer technology. So it's great to see that there's a power electronics student branch being open and give me the opportunity to give the first talk. And there are numerous benefits in becoming a member of the Power Electron Society. And as you know, that the Power Electron Society is more into, there are many advances, and we talk about a lot of things about the electrical engineering, and especially in relation to smart grids, and the smart electricity networks, and different things in electrical engineering. And all these things cannot be done without power electronics now. So it's very important now, this power electronics aspect. So just to share my screen, first of all. So I just want to give a, right. Can you see my screen? If someone can
Yes, sir.
unmute. Okay, good. Okay, so my talk is, as I mentioned, about grid integration of electric vehicles, wired and wireless, but I'm going to focus more on wireless solutions. And before I go into that, and let's have a little bit, just a quick look at the Electron Society, which I talked about. And here are the members. And the president is, as you can see, from this year and next year, Li Chuan, and then the immediate past president is Freddie Plavia, and these are the other presidents there. And joining Power Electronics Society, there are many benefits, and that include from publications and online subscriptions, and you can be in touch with what's happening, advances in power electronics arena. And especially, there are many, since this is a student branch, I'm giving the talk. There are many benefits and many activities and the mentoring programs and travel grants, and there are some competitions that's called the Future Energy Challenge, and also the PELS PhD thesis talk. Okay, that is a prize for that. So there are many benefits by joining the Electron Society. And so I would encourage those who haven't joined the society and go and join the society. So, electric vehicles. Oh, just give me a second. I just get rid of. So, electric vehicles. Everyone is talking about electric vehicles everywhere in the world. Why? EVs can be regarded as the means of future transport, and they enable efficient and clean transport, and they reduce pollution. In this context, if you look at the pollutions in different regions, especially as you can see in India, over there in the Delhi, and it's quite bad, and Dhaka, Bangladesh, and many other places, especially in the Asian region, that it's really bad. So the one way to combat this is to going for electric vehicles. And also, because of that, it's ideal for sustainable living. And on top of that, we can use the EV battery as an energy storage device or storage to offer V2X services. So when I talk about V2X, that's what I'm going to focus more on my seminar, right? In the seminar. And then before I go into that aspect, let's have a look at two other things, okay? Global EV stock and sales, past, present, and future. So what does it mean? And here you can see the electric car stock in millions in 2010. And if you look at over here, there's a blue circle here, and you can see the exponential growth after 2019 there. So this is the electric vehicle stock. And I haven't got the latest one, and from 2018 to 2019, there's a 2.2 million jump. Okay, so this is what happened in the past. Now, if you look at the future, there it is. So if you predict the future, and there are two different scenarios that you can predict the future. Okay, if you think about the worst case scenario there, and that's called the sustainable development scenario, and that is from the global EV outlook. And from 2019 to 2030, and can you believe that it is about 7.2 million in 2019 and 250 million in 2030. So this is the stock. But if you look at what happened with sales, and that was 2 million in 2019. Now it is it's going to be in 2030, 46 million. So this trend is going to continue. So if this continues, there are many challenges, but I just briefly touched some of these challenges. I can't talk about everything, given that I've got about 50 minutes to talk. And so let's have a look at some of these challenges. First one is the charging rate. That's a power level. Of course, that depends on the charging systems, and there are many different types of charging systems. I'll come to that a little bit, right? And then the electric types of the electric vehicle, and the grid, whether it can support these charging systems, and the standards, etc. Then the time that will take to charge. So now the chargers have been proposed that you can charge in less than 30 minutes, sometimes the 15 minutes, and it's called the fast charging or the DC fast chargers, or sometimes they call it rapid chargers. Then one of the problems, and the people the phase at the beginning was the range anxiety, and that's a big concern. and that is that per charge, how far you can travel, and that's a concern, and that was really a challenge at the beginning, and that of course that depends on the EV and the battery capacity. And now more and more new vehicles are coming into the market, as you can see from the new vehicles, Chevrolet Bolt and Kia Niro and Hyundai and the Tesla. They can do 250 to 370 miles on single charge, and also that's going to improve by 2030, and the EVs, and they reach an average driving range of 350 to 400 kilometers. And that's depending on, of course, the battery size. So it's improving. And more than that, and more stations. At the beginning, there are not many stations that you can go and get charged. Now, more and more stations are popping up that you can simply go and get charged. So then there are some challenges with respect to the battery, and that depends on the size, weight, cost, life at the disposal. I can't touch all these things, and let's have a look at and some of the issues. And the lithium-ion batteries, as you know, that they are the one that's being used in electric vehicles. They have high energy density, about 100 to 165 watt-hour per kilogram, but they are still heavy, bulky, and expensive. And the weight, for example, if we put in context, and the Nissan Leaf to Tesla, that from 200 kilograms to 540. Okay, so it was quite heavy. And then the cost, that was a concern right from the beginning, but it is coming down and quite significantly. And for example, in 2010, it was about 1256 per kilowatt hour, and to 2019 it is 150. They expect it to come down. That's it for the GM 2021, and that is this year to $100. And this is the prediction again. And if you look at that one, this appeared in one of the articles, there you can see that the prediction there is more in the same ballpark. There you can see it's coming down, and then by 2030, and as you can see there, it's going to come down to about almost to 50. That's the prediction is going to be per kilowatt hour. And then we have some concern with regard to the lifespan. How long can we use that one? It's normally about 3 to 8 years, or 100,000 kilometers. But more and more new technologies are coming up. So in other words, the battery technology is improving. For example, just a minute. Can you hear me? Hello, can you hear me?
Yes, sir.
Yes, sir, you're audible.
Okay. Yeah, because something might. Okay, so you can see the new technologies, and the Chinese car battery manufacturer, and they announced that they can produce, and that is capable of powering a vehicle up to 1.2 million miles. That's pretty good. So that is about 16-year lifespan. And not only that, and some other universities are working on new technology. This could be better voltaic batteries, and they say that they can have constant current lasting for thousands of years. And this company, that's called QuantumScape, and they are producing these particular solid-state batteries. And they say that they are lighter, high energy density, they can give more range, lower cost, and fast recharge time, but it is still a little bit away to produce it. And the latest being that this appeared on the IEEE spectrum, as I recall that, and this is a new battery technology, and that's called based on lithium-ion cells with nickel foil, and they are ideal for electrical vertical takeoff and landing and aircrafts. So you can see that the battery technology is improving, so we can expect that it's going to be better. Then if you set aside the issues or the challenges in relation to the electric vehicle side of things, but there are some other challenges impact on the grid, because the energy has to come from somewhere. So here's the peak EV demand by 2030, and there you can see in gigawatts, and in this is a prediction, and that's from the EV Outlook. And there you can see even in charging in China, it's about 60 gigawatts, and that is about 12% of the demand there. And even in India, it's going to be about close to about 15 or 18 gigawatts, and it's about going close to about 4%. And that's going to increase. So what does that mean? So these are huge challenges. The energy has to come from somewhere. We need to do something about that. Can we actually cater for this demand using the existing network? Can we do that? And to what extent? So the prediction is that we can reduce to meet this demand, okay, just by 5% through energy shifting. That's the optimized charge. There are some charging strategies, but nevertheless, these are challenges. Then the other one is, then more and more countries are moving to full electric by banning manufacture of petrol and diesel vehicles. And that's happening everywhere, okay? And this further compounds the impact of EVs on the grid because it needs to be charged. And for example, in the UK, and they wanted to ban this by 2040. Now they have brought it by 10 years earlier, so they want to do it by 2030. And I know that China announced the same thing quite a while ago, and you can imagine the number of cars in China, and if they stop producing diesel and petrol cars, and that's going to be a huge impact on the grid, and that's going to happen in 2030. And New Zealand recently they announced that too. So not only that, and if you look at this is what Honda very recently announced, and if you look at on the top left-hand corner, and by 2030, 40% of their market is going to be from electric vehicles, electrified or fuel cell. And 2035, it is 80%, and they want to, in the 2040, completely electric vehicle, fuel cell. Not only the electric vehicles. And look at the bottom, right-hand corner there. And even their e-scooters going to be electrified there. So what does that mean? There are huge challenges. Are we going to use the same? Energy has to come from somewhere. That is one aspect. And the other thing is, can the network cope with this energy demand? So in other words, that's going to be inevitable. So we need to do some upgrades on power networks, substations, and infrastructure. So that's a different thing. I normally talk about that too, what things people have been doing. But that is more into some of the challenges on the power system side. Okay, so what I'm going to do is now to talk about some of the technologies. Now let's have a look at EV. And I mentioned that earlier, EVs can be used as an energy storage to offer V2X services. So you must be wondering what V2X. Before we go into that, let's have a look at the energy storage. So this is the world electricity supply by storage technologies. So by looking at it, you can see that you don't have to look further into the future. By 2030, even 2025, and the storage technologies and the EV storage will dominate. There you can see that ranges from long duration storage, scale lithium-ion batteries, the pump hydro, but then EV storage is going to be the dominant storage. Okay, so what does that mean? This means this installation of bidirectional chargers in commercial and workspace settings will become standard. In other words, yes, if you're going to use it as energy storage, you have to retrieve the stored energy too. So the only way that you can do it, you had to have the bidirectional capability. That's how I've been working on to how to do it wirelessly. Okay, so then let's have a look at what is this V2X concept. So the V2X concept is that, this is not new. Actually, you must be knowing V2G, vehicle to grid or grid to vehicle. So what we do is that in the peak time, off-peak time, when the tariff, the rate is low, that you can charge the electric vehicle because at the lower rate. And when it is at the peak demand time, you can put it to the grid or you can use it. That's called the V2G and G2V concept. That's been extended to build into home to electric vehicle or vehicle to build into home there. You can power your home or the building and through electric vehicle. That's been extended to further, and a charging bay, you go there and vehicle to vehicle, you can exchange energy. So what is important, you can see that the arrows are going back and forth. That is the bidirectional. In other words, you can charge, then you must be able to discharge as well. In other words, you store, retrieve energy, and as appropriate. So what is essential? Now you can see on the left-hand side is the grid or the energy source, and the right-hand side is the electric vehicle. So what is essential for V2X compatible electric vehicles? And that is you had to have a bidirectional charge. In other words, you must be able to energy flow you must be able to regulate the energy flow in both directions there. So it could be either it could be wired or wireless. Okay, so in other words, charging technologies, are we going to go wired or wireless? So what's the means of charging? And if you go to wired, and you can see it's conductive charging, it's very easy. You can just connect the cable there. There it is. Relatively simple and less infrastructure, and the standard is JSAE J1772, and it's in use. Then if you go to wireless, yes, it's very good, robust, safe and convenient. It doesn't matter whatever the adverse weather conditions, ice, water, it doesn't matter. You can just go and park the car. But with respect to wire, considerable infrastructure change, and you had to have some dedicated hardware. And also standard just been released, and the SAE J2954, in my opinion, cannot be deployed everywhere if you think about that in third world countries. Okay, and it's very difficult to deploy it, but it's going to be in urban places, and it's going to be very convenient to use wireless charging. That's going to be the future, and this is still at the development stage, and it's been tested, and now the car manufacturers are working on that. And here's the standards of the wired charging. There you can see it goes from AC level 1 to AC level 2, DC level 1 to and DC level 2. And the AC level 1, AC level 2, the amount of the charging rate, that the power is lower than that of the DC level. So consequently, the charger can be on board, and that's why it's on board. But when you go to high power charging, you can DC charging, of course, the charge is quite bulky. So consequently, it's off-board charger there, and that is provided by the commercial entity there. Okay, so you can see the charging rate, the input level there. So the equivalent, the European standard, that is IEEC, and very similar to the Chinese one too. There you can see mode 1 and mode 2, and then what you can do, charge, and then of course mode 3 and the mode 4, that's called the DC rapid charging. There you can see that it's going up to about 600 volt to 400 amps there. So it's a very fast charging, and the people are at the moment talking about developing up to 500 kilowatts charging rate. So I don't know what's going to happen to the battery, but they are working on that as well. So here are the charging systems, and the AC level 1 and level 2, and as you can see, I think that is called, I think that is level 2 or level 3. Also small charger, but it's off-board charger, and this is the CHAdeMO one. And there you can see, I think that was a 25 kilowatt one, and that's a Tesla one too. So that's about wired charging. There are some protocols. You can't simply connect and charge. There are some protocols and the connectors and etc. AC and DC combo, the connect chargers and etc. So I wouldn't go into those details. Okay, so that's a little bit about wired charging. So let's go to wireless EV charging technology and how we can do the same thing without any physical connections, or in other words, without any cables. So the wireless charging, that's based on inductive power transfer technology. In other words, here we have the grid, that's the AC, and that's a low frequency. What we do is from the low frequency convert it to high frequency, and then we have sort of a coil, and that is buried in ground, and that's called the ground pad, or we can call the primary there. Then we excite that coil, and with the high frequency current, that will generate a high frequency magnetic field, and the car comes and parks, and there's another coil mounted underneath the vehicle there, and through the magnetic coupling, because there's a magnetic field that's produced by the ground pad, and through the magnetic coupling, and the power transfer takes place. That's why it's called the inductive power transfer technology there. So inductively, you charge the car battery, and there you can see from that arrow there, it is only one direction. In other words, the energy is coming from the grid to the electric vehicle. In other words, you charge the electric vehicle and taking energy from the grid. Then about more than 10 years ago, I started working on what about we can do both directions, that we can charge and discharge wirelessly. So that's how I started developing this technology here. So you can see I can regulate the wireless power charger, the transfer very efficiently. So this is called the stationary. Why the car comes and parks, the car stops, star is not moving, but the future is going to be dynamic. And there you can see some dedicated lanes on the motorway, And there you can see on the motorway there, on this lane there, there will be some charging pads, the coils, that's the primary. Okay, that's the one that's powering or charging the vehicle there. So they are buried in ground there, and then as the vehicle moves on top of along that charging lane there, on top of the pulse of charge will come. So a car can move at 100 kilometers per hour, and then you can charge the car as nothing, that is in motion charging there. So you must be thinking that this is not true, but this has been already tested. That's what the future is going to be, but there is no standard at the moment. It's being developed. So what's the standard for stationary wireless EV charging? That's called J2954. LDEV stands for light duty, and the HD stands for heavy duty, and they look into it. And this specifies safety, performance, interoperability, communications, and the control, as well as how do we detect the foreign objects or the living objects and the emissions, etc. And what frequency does this power transfer take place? It takes place at 85 kilohertz. This is what the electric car manufacturers agreed to. And we have flexibility of changing the frequency from there's a window 79 to 90 kilohertz, but as I was understand that you cannot change the frequency while you are charging. Minimum target efficiency should be 85% when it is aligned, and if it is off, it's not aligned, the two coils, and then it has to be at least 80%. And these are the classes of charging. This is the power level that's given as the VA rating 3.7 to 22 VA. And there's some ground, what is the charging distance and etc. It's all in the standards there. So I wouldn't go into some of the details, the different coil structures and etc. Because given that I have a short period of time to give this talk. So bidirectional. So how do we do that bidirectional wirelessly for V2, especially for V2S? So this is the atypical bidirectional WPD system, and this is called the ground assembly. Because that's on the ground, and that's the one that we use to charge the car. On the right hand side is the vehicle assembly. So what does the ground assembly have? And there you can see that's the grid, and that is at the 50 or 60 hertz, low frequency. That's being converted to high frequency, right? So in order to do that, we convert the low frequency to DC, and then the DC into high frequency, the 85 kilohertz. And then we have this compensation, which I will talk in a minute, what it means. And these are the coils that I was talking about. Sometimes people call it transmitter, receiver. Sometimes people call it pads. That whatever those are the coils there, and they're separated by an air gap. They're coupled through the mutual inductance M or mutual magnetic field there. And if you go to the vehicle side, and it's a very similar thing there, and we have a compensation network there. Then of course this is the power transfer or the charging takes place at a higher frequency. It needs to be converted into DC there. That's the EV battery. So if you take that part there, if you expand it, this is what it comes with. Now, what is this compensation? So you can do that, but if you do that one, there are some losses because the S or the VA rating of the converter is going to be very high. You had to give more current because from the supply needs to give reactive power as well as the active power. But if you can provide the reactive power or compensate for the VAR requirement of the coils by connecting capacitors either series in parallel or in the combination of that in a manner that they resonate, then we can reduce the VA rating. Right? So basically, when you look at that one there's a minimum VA rating, same as the active power there, the unit power factor. So that is why all these IPT circuit or wireless power transfer systems, and they are compensated. They are resonance circuit there. So here what I have shown here in this diagram is the LCL. And here you have the inductor here because of the voltage source that is converted to current source. There's a parallel resonance circuit and the both sides there. So basically these two circuits, and they are resonating at 85 kilohertz. We choose these capacitors and inductors in such a manner that it is resonating at 85 kilohertz so that the VAR requirement is basically zero. So you can transfer power very efficiently and with the minimum VA rating. Okay, so this is what it is, and you can see, that the right hand side there, and you can actually control that converter. You can have a rectifier if you want, but there are some control techniques. You can have active converter there. You can control the impedance. There are a lot of things that you can do. Okay, so you can control that impedance there. So either way, but if it is completely tuned there, then we can write down this equation here to power transfer. By looking at it, you can see the output power dependence on the two voltages produced by the converters and also the phase angle in between them. So how do you control that? This is happening at 85 kilohertz, right? So this is an 8-order system. This is a resonant or tuned system there. So these two sides are synchronized, but we can't do PWM because it's taking place at 85 kilohertz. We do the phase modulation to control the voltages. So what do we control? We control these two voltages, two phase modulations, and we keep this angle at plus or minus 90 degrees to keep the VAR requirement to minimum of 0. So in other words, on the right hand side, if it lacks the voltage produced by the primary side and the power transfer, power flow is from the left side to the right side, in other words, you're charging the electric vehicle. And if it is leading, it's the other way around, as you can see from the bottom diagram here. So this is what we built a long time ago, and there you can see the gap is about I think about 400 millimeters as I remember, and there you can see the energy is going both ways there. So since that we have come a long way. Okay, so I'm going to talk about some of the technologies that we have built. And this is how do we do this V2X concept? In other words, how do we have this binary G2V or V2G? There you can see, as I explained before, on the top, and this is the primary side converter. The blue is the voltage. That voltage is leading that of the electric vehicle side converter produced voltage there. So consequently, EV is getting charged, and this is at 3 kilowatts. And this is another one, the EV now supplies. By looking at from the red arrows, you can straight away, you can see that the grid side voltage is lagging, and that is produced by the electric vehicle side. And here's another one, the multiple electric vehicles. There you can see that in the different ways, so all the voltages are like a square wave there. One is lagging and one is in phase. So basically one is idling, one is receiving energy from the grid, whereas both electric vehicles in the bottom case giving energy or putting energy back into the grid. So this is, there are many techniques now we can do, okay? And now let's have a look at some of the practical issues. Now, I mentioned that when the car comes and parks, the two coils needs to be aligned. If it is not aligned, there are consequences, okay? So what are those ones? The one is the mutual inductance will change. Sometimes the coil inductance may change, but given the high the reluctance there, the change may be low, but nevertheless, if it is mistuned, what will happen? It's not resonating. So what can we do? Then the power transfer is going to be affected. You may not be able to regulate the same amount of power. So what we can do if it is the misaligned? So that's so the car comes and parks, and they are subjected to prone to lateral and longitudinal. So when that happens, you can see the mutual inductance will change too. Could be some inductances as well. But when that happens, as I explained that, so we won't be able to transfer power efficiently at the same level. So what can we do? There are two solutions. One is to do a passive control. We don't do anything. We design the pad system or the compensation systems in such a manner that combine them and it is tolerant to pad misalignment. So I'll show you what actually happens. There it is. And you can see this is the system, this is the hybrid system. And what is meant by hybrid is there are two different compensation circuits. Because each compensation circuit have different characteristics, but they're complementary. If they're complementary, then what it means is, right, when they combine together, and we can actually somehow or other negate the effect of the power, the reduction in the power due to pad misalignment there. So mainly because the nature of the reflected load is complementary each compensation network, because they have different characteristics. So if we can make use of this characteristic, we can regulate the power despite of any pad misalignment there. So this is what it means. Here's the power output from a hybrid system or a tuned condition there. There you can see on the right hand side, and from the one compensation network, it is directly proportional to mutual inductance, that is M. Whereas from the other compensation technique, it is inversely proportional. So if the mutual coupling reduces, the power in one decreases, whereas the power in the other one decreases. But if you combine them together, they will cancel out. They're complementary, this characteristic. So this is what's been developed like that, and I have a video for that some our group did, right? There you can see the one is the LC tune, that's mean the red one, and that is the series tune. So the compensation network there. In other words, there you can see that with the series tune IPT system, and as the distances in the coupling changes there, the power increases, whereas the parallel tune it reduces. Now, if I combine them together, you can actually have more uniform power output there. So it doesn't matter, you don't have to do anything if you have a system like this, and if you combine and these two compensation networks, then you can still, the pads are misaligned, but your power transfer of the charging rate is more or less constant. Okay, so that is one way. And the other way we did recently, 2 or 3 years ago, is active control, right? We don't have to have, we can have a simple compensation network, but we use the control. We control the converters in such a manner that we can actually compensate for the pad misalignment. So this is what we did. Okay, it's called the optimal multivariable. We control everything. Okay, that is with the impedance matching to negate the effect of pad misalignment or change in the mutual inductance. So what are the things? We have 4 control variables, 2 voltages, 2 were produced by the converters. What else? Frequency. But remember, we can have a little bit of degree of, we have the flexibility to control the frequency. Remember 79 to 90, though it is we had to look into one frequency, but we can change the frequency there. And the other one is the voltage in between the 2 voltages produced by the converters. But the question is this, there are endless combinations depending on the DC, the voltages. Okay, there are endless combinations for any given power, and the coupling is mutual inductance variation there. So the question is, how do you determine the optimum value? With impedance matching. So I can control the second side converter in a manner that whatever happens, the misalignment, I can still regulate power, not regulating power at maximum possible efficiency. So how do we do that? We came up with this idea. Okay, so what we did was we came up with this 2-stage optimization process and to find out what are the best values of these 4 control variables, okay, under that condition. So what we did in the first stage, we optimized the AC to AC conversion stage, and that is from the outputs of the 2 converters, that is AC, right? And we do impedance matching to maximize the efficiency there. There it is, that's the AC impedance that is seen. And then what we do is we optimize it, and we can show that theoretically it becomes actually, if we make sure that is omega times M, okay, for different variation of the mutual inductance or whatever frequency that you're operating at, and then we can have the optimal efficiency, AC to AC efficiency. So once we know that, we have maximized the efficiency with the impedance matching, and then we can find out what would be the voltage that I should produce at this converter here, and that is beta. Okay, so once we know that one there, then we can find out what would be the relationship between the current and the voltage of that converter in a manner that I can have zero voltage switching. So why do you want to have zero voltage switching? I can minimize the switching losses there. So the second stage, I optimize the operation of the primary and secondary converter with zero voltage switching there. So there it is. So I can find out what would be this angle. Okay. So in other words, I can control the impedance of the secondary side converter. And by knowing that one now, theta S, then I go to the next one. So I want to actually reduce everything on the secondary side. There's VAR requirement on the secondary side there completely. We don't want to give any VAR there, only unity power factor there. So in order to do that, I change the frequency here. So that frequency gets locked into the secondary side. So it keeps on iterating, right? Going back and forth, and will converge. And then we control the voltage depending on the power, and also to get the zero voltage switching on the primary side converter. So this is an iterative process. You keep on doing that, it will converge it to one place. And this was implemented. I show you some of the results. This is one of this worst case scenario, 200 watts. And this is the pads are misaligned. As you can see, the mutual inductance has changed quite a lot. And we have compared that with two different control methods. One is called DPS, that's called a dual phase shift. That means controlling 2 variable, TPS triple, and controlling 3 variable, alpha, beta, theta. That means 2 voltages in the angle. Then our one is controlling all possible 4 variables. There you can see that for the same power output, for the same misalignment, we can we ensure the power is regulated at minimum current there. So you can see that is how good it is. And just to show how this is, and there are some variation, what would be the effect with different voltages at the DC bus, and I can't talk all these things. And here you can see the efficiency. 60 microhenries to 21 microhenries, there is mean misalignment there, and in the power transfer is up to 1 kilowatt. There you can see the blue one is the optimal control with 4 variables. In all these cases, that gives the highest efficiency, okay, in comparison to whatever any other reported schemes. So that's a little bit about, there are many things that we have done, the compensation, the control techniques, and this is something that we have. So, but I cannot talk everything, as you can understand. Now I'm going to talk a little bit about grid interface. That is on the front side, okay? There it is. Now what I talked about is this part here, DC to DC. So, but we have this part here. Then you can see that the low frequency is converted into high frequency using AC to DC and DC to AC. 2 converters there. So we thought that can we do that? Combining these 2 converters using matrix converter. Of course, the matrix converter is not new. That's been happening, but doing this as a resonance circuit at high frequency, 85 kilohertz, not 50 hertz. So basically from 50 hertz, we convert directly to 85 kilohertz, and also this resonance circuit, and also we ensure that the power flow can be in both directions. So we implemented this. This is one here. Here's the matrix converter, and to achieve this feature. So it reduced number of conversion stages. It doesn't require large filter inductor or DC link capacitor. Direct conversion there. So now if you look at it, it's complex, a little bit of control. So what we have is a constant voltage. So in order now from this 50 hertz constant voltage source, we have to convert that into 85 kilohertz, and also we have to control the power flow in the both direction. Not only that, the magnitude of the power too. So how do you do that? So the only way we have the variable is to control the current. So in order to control the current, if you can get some expression for the current, and that's called the dominant grid current. And there it is. Now how do we control that? And we had to control that either in phase of the grid voltage or out of phase of the inversion. So how do you do that? So by controlling that, we can regulate the power output or the power coming back from the electric vehicle to the grid side there. So there are 2 variables there, phi 1, phi 2. In other words, we control the phase shift to control the amount, the magnitude of the power. And then we control the angle between those 2 voltages produced by the 2 converters to control the direction. So we keep it at 90 degrees. Okay. So this is what we implement on the left-hand side, and these are the experimental results. That's the left-hand side, the simulated one, and the right-hand side, the experimental one. There you can see the blue one is the grid voltage and the green one is the grid current. There you can see they are in phase. So that's the power transfer takes place from the grid side to the electric vehicle side. In other words, the electric vehicle is being charged, and there it is discharged. There you can see they are out of phase. And that is in perfectly very good, and it's more like a unity power factor. There are some of the characteristics, the quality, and the THT, and that is within the standards, and also power factor is very close to, and the efficiency is about 80 to 88%, but we haven't actually maximized the efficiency in that case. Then we did something a couple of years ago, the new one, and it's called the versatile wireless vehicle to grid home interface. So this is what it is. So when you want to charge the electric vehicle, you have to connect it to the grid, and there you can see that the this part is the typical wireless interface, or sorry, wireless transfer interface, or the module there, that is DC to DC, okay? So basically DC is connected to high frequency connected to DC there. That is what I talked before at the beginning. Then still, energy has to come from somewhere, it's coming from the grid. Now the grid is okay. Now this is the whole thing is your home here. So you have your household loads, and they are non-linear, and they need these ones there. So the active power of the load and the harmonic power as well as the reactive power there. Okay. So normally the grid tie, typical, the converter, that gives only the active power that is required to charge or discharge the battery. That's all. That just handles that part there and in both direction there. So this is called a typical low frequency grid tie converter. So when that happens, everything else needs to come from the grid. And you can see on the top, the grid takes care of the load as well as the load active power, as well as what is coming from plus or minus the electric vehicle, whether it's been charged or discharged. And then all the reactive and the harmonic power requirement is made by the grid. So we thought that, well, can we actually, since we have the grid interface already, whether we can with the power quality interface there, so that grid doesn't give anything, grid only gives the active power, and all the harmonic and the reactive power is taken care of by the grid interface of the electric vehicle there. Not only that, as you know that normally this DC bus voltage is kept constant, but we thought that we can have an adaptive control in such a manner we control the DC bus voltage depending on the energy requirement. By doing so, we can ensure that we can operate the wireless power transfer module with zero voltage switching, and if we can do that, we can increase the efficiency or reduce the losses there. There it is, that enables zero voltage switching operation. Actually implemented this system, and this system can be operated in 5 different modes. And the first one is, let's say, the active power field, and that is the grid. And the grid is actually powering the house, but all the harmonic power is going from the interface. And there's no car there. You don't have to have a car because the car is gone, right? But still the power interface has to be there, charging interface there. So it takes care of the reactive power and the harmonic power. And then the grid is actually charging the electric vehicle as well as the supplying power to the grid, but only the active power, for the household, but all the harmonic power and the reactive power requirement of household is made by the power interface. And then this is the vehicle actually is powering both the house and also the putting excess energy into the grid there. And this one, vehicle and grid, is supplying the household needs, and because the vehicle cannot do it, doesn't have enough energy, so therefore it is supplemented by the grid, only the active power. And this is the islanded mode. There's no grid at all. There's no electricity network, but it's being powered by whole household need, powered by the electric vehicle. It's called the islanded mode. So these are the modes, and there you can see the vehicle and the grid is now powering the home there. There you can see that the first part. And there you can see the household load has about THD about 48%, 7.5, that's non-linear load. And there you can see that the 430 watts of active power is needed, and 250 is coming from the electric vehicle, whereas 180 is coming from the grid. And the other important thing is grid doesn't give any reactive power. All the reactive power is and the harmonic power made by the power interface there. Okay, or the electric vehicle interface there. So consequently, you can see power factor of the grid side is almost unity, and the THD is very small too. And here's the islanding mode. Obviously, you can see that on the grid side, the current is zero. So everything is made by the electric vehicle, the active as well the reactive and the harmonic power. And there you can see the grid power is zero. So obviously the current has increased. What is injected, because everything is taken care of by the electric vehicle. So this is another mode, that's called the active power filter, and there, of course, electric vehicle is not there. So consequently, and all the reactive power, there you can see the active power is made by the grid, whereas the reactive power is made by the power interface, grid interface there. And then again, you can see the THD and the harmonics, the power factor of the grid is 1. And this is the grid, and the grid is actually charging the vehicle as well as taking care of the load of the household, and therefore the grid current has to increase. As you can see, it has gone up, and there you can see, and the grid power has increased to taken care of the active load of both the household need and the car, and still the reactive power is made by the electric vehicle. So this is the experimental, the results of what we have done there. There you can see how, this is what I told you about the DC voltage is changing depending on the power requirement there. There's adaptive control, it's a prototype there. So now the question is V2X, okay? And you must be thinking, is this a reality, or it is real and it's going to happen? And actually, Nissan Leaf, and that is called Leaf to Home, they released this in 2012 or 13. They've been working on that, but that was not to be able to connect it to the grid. It's only you can power your household. So it can power household for 2 days. That's the energy, and that's going to leave to home system, because they didn't still, I don't think that they have a standard to you can put the energy back into the grid. But most electric vehicles coming now into the market, they are V2G compatible. Not only that, you can go to CHEDEMO website. There are already V2X certified products that you can buy. And not only that, Honda V2G, and they signed an agreement with Y2City, and we are working with Y2City in 2018 to develop. There you can see the wireless V2G system there. So with that, I'll conclude my lecture. I'm quite happy to give answer any questions if you have any. Thank you.
Thank you, sir. It was a pleasure to attend, and you helped everyone to articulate novel aspects of grid integration of electric vehicles. Now it's the time for Q&A. So participants, if you have any queries, feel free to ask in the chat box.
Looks like no more questions.
Yes, sir. The first question is, what is the efficiency of wireless energy transfer compared with cable connected charging?
At the moment, people claim up to 97%, and some claim that they have achieved 97%. And as you can see from the standards, the minimum that you should have is when the line's 85%. So most systems can have more than 90%. As far as I know what's been built here.
Thank you, sir. The next question is, how vulnerable are people with pacemakers or other electronic implants that would be affected by electromagnetic fields, and how do you protect them?
Yeah, when this is, and if you look at the standard, I touched that part. The standard actually covers all these things there, and the magnetic field is actually the magnetic structure is designed in such a manner that are within the guidelines, that nothing will be affected, and also it is shielded, nothing comes out there. So it is within the standard. I think it's about 25 microtesla within 1 meter or less than 1 meter from the pads, and therefore there are no issues whatsoever there. Even the electric field is within the standards there. So with shielding, and also these magnetic coils, all these charging coils are designed in such a manner the leakage flux is minimal. And also there are techniques that they can, if something in between, I just touched that one, living object detection and the foreign object detection. So what it means is when you're charging something in between the two pads, and they can detect that too.
Thank you, sir. Next question is, how can we overcome the drawbacks of wireless charging? That is, how can we overcome the drawbacks of wireless charging? That is, cost and speed.
Cost and speed. What is meant by the speed?
Sir, it was asked by one of the participants. I will clarify.
Yeah, I don't understand. Cost is, yes, could be costly, but I mean the convenience is the biggest things, and also it's how it can be used in different hostile environment there. So that is something that you have to have a compromise. Time taken for charging. Time taken for charging is nothing to do with the wireless charging, right? At the moment, it is the standard is up to about, I think that's a 22 kVA, right? And that is to do with the charging rate. Whether it is wired or wireless, that all depends on the time for charging, depends on the power rate, charging rate, power level.
Sir, next question is, what are the particular challenges or opportunities wireless charging technology presents for EV racing car builders?
I think some are working on that too, and I showed you some, perhaps that may be a future, and I show you some, the in-motion charging, and it's been tested at 100 kilometers per hour and 20 kilowatts of pulses, or the 25, yeah, energy pulses, kilowatt, power pulses. So that is being tested, I think, 4 years ago. So yeah, that is very possible. A lot of people are working on at the moment with dynamic charging.
Okay, sir. Next question. Are there any plans to implement the technology into the upcoming Formula E electric motor racing series?
I can't comment on that, but I know that they have electric ones going, but it may be future, but still there's no standard as such. So first the standard has to come. Okay. The standard has been released for stationary charging, not for in motion yet. And also I think the standard next one is going to for heavy duty vehicles, much higher power level. So that is next, and perhaps in conjunction with that, and they might release in motion, but that is also dedicated. Right, the lanes be there, maybe a little bit away. But for racing, it could be earlier. But I can't comment on that. I don't know. I don't sit on the committee, as I'm not a committee member. That come there.
Okay, sir. Thank you. So all the queries are addressed, and then let's conclude today's session. The feedback form is provided in the chat box. Participants do fill it out. Now, let me invite Dr. Vijda S. She's the counselor of IEEE SB NSSCE and a great support to all our activities. Over to you, madam.
Wow, existing. Sir, thank you so much for taking up your time and enlightening us on this idea of charging and electrical vehicles. And I think most of us would have got an idea of what it is and how it is going to work, because this is the latest or hottest topic that is there in EV field also. And I actually am really proud of my SB, because all these societies are on a verge of conducting one or the other DLPs to learn from the line at the lines. Then is what is actually the theory. But though we can't go there and learn, but yes, we have taken sir's time, and then sir has given us the opportunity. I mean, sir has actually given us a good idea about all these things. So we've learned from that. So this is the main thing that we have in our SBs also. We are trying to bring in lots and lots of DLP, so that, apart from we teachers teaching the basic concepts, somebody is there who has got an expertise in the field. And if he is able to share his ideas and thoughts, that can be a basic for the development for the other students also. So thank you once again, sir. And I congratulate all the team members who had worked hard towards creating this DLP. Thank you, kids.
Thank you, ma'am. Next, for a photograph, I request everyone to turn on your cameras. Okay, thank you all. Next, let me invite Ms. Sharika P., Chair, IEEE PELS SBC NSSCE. Over to you, Sharika.
Good morning and good evening, everyone. Technology, like art, is a soaring exercise of the human imagination. I would like to take this moment to share my gratitude in conducting the Distinguished Lecture program on grid integration of electric vehicles, wired and wireless solution. Professor Udaya K.Madawala, who is a wizard in the field of EV, has carried out a remarkable session today. Thank you, sir, for joining us. And please do accept our small token of gratitude for sharing your time and wisdom with us. Vivek?
Okay. So, I would like to thank that gave me the opportunity, and I hope that's been informative and it was a pleasure. If anyone wants to ask any questions, or anyone else needs some support, and just feel free to write to me. Okay.
Sure, sir.
It's a pleasure. Okay, thank you very much. Okay, then.
Thank you.
Have
Thank
a
you,
good
sir.
day. Okay,
Yeah.
bye.
Thank you, sir.
Bye.
Thank you.
Thank
Bye.
you.
Bye.